Okay, so today's presentation is the principles of human spacecraft active thermal control system design. Today's presenter is Dr. Eugene Ungar. He's a senior thermal and fluid analyst in the Crew and Thermal System Division of NASA Johnson Space Center. His 30-year career has covered a wide range of thermal issues, including development of the ISS active thermal system and the conceptual design of the Gateway active thermal system. He received his BS in Mechanical Engineering from the University of Cincinnati, MS in Mechanical Engineering from the University of Kentucky, and PhD in Mechanical Engineering from the University of Houston. Go ahead and welcome Dr. Eugene Ungar.
Thank you, Carlos. I'd like to thank everybody who's joining us for this presentation. I know, since we're the first ones who are doing a presentation at TFAWS this year, there have been a little bit of technical issues, but I think we've got them mostly worked out. As Carlos said, if you've got questions, go ahead and put them in the chat button. We've got some places in the presentation where we'll pause and we'll try to go through the questions that we've gotten. As Carlos says, I've been around in the spacecraft business for a fair bit of time. When I first came to NASA in 1987, we were in the process of designing the space station Freedom, and we were working on the active thermal control system for that. We were a two-phase thermal control system, active pumping liquid ammonia, vaporizing at the heat acquisition sites, condensing in the radiators. Talk a little bit about that as we're going through. So I go that far back, also lived through the space station redesign where we actually were looking at some options that used a Freon-21 pumped fluid loop, just a single phase pumped fluid loop. Have worked on some on the Orion thermal design, specifically whether we were one fluid or two fluids, and trying to drive those designs to the right answers, and built the Gateway conceptual active thermal control system design. And so what I'll be talking about here is this presentation was put together originally as part of what I call my Fix and to Go tour. I'm part-time retiring at the end of next month, and so my availability is becoming more limited. And one of the things I'm trying to do is to put together packages and kind of pass on some of the things that I've learned in 30-odd years in the spacecraft business, so that younger folks and other folks don't have to go through the same pains and going down in all the blind alleys that I've gone down, and to try to help with that. So first thing we've got is a disclaimer. This is the legal office made me put it in. So when I talk about Golden, that doesn't mean that NASA is endorsing Golden. So anytime we use a trademark, we're not endorsing it, we're just identifying as a trademark. And I have no idea why the legal guys maybe put this in, but it is in here to make it. So when we talk about active thermal control systems, generally we talk in thermal control, there's a big area, and of course here we're at the Thermal Fluids Workshop. So when we're talking general thermal control, we're trying to maintain crew and equipment within specified temperature ranges over the range of operating power and environments. And more specifically, when we talk active thermal control, we're talking using flowing fluid to acquire the waste heat and to pump that. So we pump the fluid, acquire through the fluid, take it out to radiators or someplace and reject the heat to space, whether it's to the vacuum of space using a sublimator or an evaporator, or using a radiator to reject it to the cold of space. So here we're really going to talk about active thermal control systems, because that's my field and that's what I do. So I think I've talked a little bit about this. So what we're trying to do here is just kind of give you all an overview of the principles and ways that we go about designing active thermal control systems for human spacecraft. I'm going to include some tricks, some tips, and some techniques. The alliteration is easy to write, hard to say. Also going to give you my opinions, some shortcuts that you can use, and informed prejudices. And when I say informed prejudices, that's really things like if you're putting together some sort of a conceptual design, somebody might ask a question of why didn't you do it this way? And there's a reason that you didn't do it that way. And it may just be because, I know off the top of my head that that's not the right answer. And that's what I think of an informed prejudice. Like for example, when we were designing the Gateway active thermal control system, I believe one of the young project managers said, well, don't you need to do a trade study for a two-phase system? And I'm like, no, this is a small spacecraft, low power. we know that two-phase is not the right answer. Single-phase pump loops are the right answer for this one. All right, so when we're going to start looking at an initial design and trying to analyze a human spacecraft ATCS, we've got to look at a lot of stuff. You know, you start looking at, a lot of them are binary choices, a lot of them are choices where you've got just a whole plethora of options. You know, for example, am I going to do an internal-external loop pair where I've got a single fluid loop inside or a fluid loop inside, a different fluid outside, both of which are pumped? Or do I try to do a single loop system where I've got the same fluid inside and outside of the spacecraft? I've got to choose my coolant. So we'll talk about what are the optimal fluid properties. What are you really looking for? And we'll also talk a bit about non-toxic fluids and what that really means. You know, I talked about single and two-phase systems. You got to make a decision. Am I single phase or two-phase? Do I want to use flow-through radiators or do I want to use heat pipe radiators? And this was also a decision we made fairly early on in the space station program, and I'll talk a little bit about that. Use body-mounted or deployable radiators. What do we want to do in terms of the radiator return temperature control? You know, typically when we're setting set points on this system, we want to be able to supply coolant at a particular temperature to our users. And part of that is going to be our radiator return temperature. So we're going to set that, but how do we do it? What's the right way to do it? And then we'll just talk a bit about radiator performance. And we're going to talk about everything that's in this list. And if I get off topic, we'll probably talk about some other things too. So the first question is one loop or two. And in the Apollo command module, there was a single loop inside and outside the spacecraft. They used a water ethylene glycol mixture inside, and that flowed through the radiators outside. And that was the way that Apollo did it. But once we moved away from Apollo, and we moved away from a vehicle that was going to be in deep space, and they also, one of the other reasons was that they had a bear of a time getting the stagnation radiators on the command module to work and to work properly. So when they built the space shuttle orbiter, they went to two loops. They went to a deoxygenated water loop inside with all stainless steel tubing, and every surface that touched the water was stainless steel, and Freon 21 on the outside. And there, with Freon 21, you can use aluminum it's compatible, but inside they were all deoxygenated water. And as an aside, one of the reasons they went to deoxygenated water and stainless was on Apollo, because mass was so important, the tubing was aluminum. And the ethylene glycol water mixture had inhibitors, but what they found was that if the loops were stagnant for any period of time, if the pumps were turned off, the inhibitors got depleted locally and you got corrosion, you got crud in the system. And so they wanted to get away from that. And so they went just to pure water, deoxygenated stainless steel. And these deoxygenated water lasted for 30 years with no corrosion. There was no issue. You'll see that sometimes we react to problems that we had in the previous spacecraft, and maybe we overreact, but we solve that problem. And so you're always solving the problems that you had previously. For space station, we used treated water inside and then used ammonia loops outside. And the reason for ammonia is it's actually a better heat transfer fluid than Freon 21. It's got a low enough freezing point that it works okay in low Earth orbit. If you're working with the space shuttle, where the space shuttle was designed to have the radiators point at deep space pretty much for hours on end, you need to have a lower freezing point fluid than ammonia. But ammonia worked just fine for International Space Station, continues to work today. On Orion, we reacted to the issues we had on space station where we were always worried about freezing the water loop. And so inside in the internal loop, they went to water propylene glycol and dropped the freezing point by 10 or 15 degrees. And then outside, they used HFE-7200, which is actually kind of a Freon 21 analog. It's a fluid that's a lot like a Freon. But of course, Freon 21 is an ozone depleter, and it's not available anymore. And so that's what they're using on Orion. Commercial crew vehicles, they're single loops. They found that there are advantages to being single loop and that they can be single loop. So there's always advantages to being single loop. And then the question becomes, can you do it? But now the question becomes, what's really the best choice? Is, as I said, historically, we've chosen practically everything you can imagine. But what's the real best choice here? So if we look at simplified schematics of single loop systems and two loop systems, on the left, we've got a single loop system, and it's fairly simple. You've got a pump that pumps through possibly a heater that's used to maintain heat load if you don't have enough. The liquid goes out either through a radiator bypass or through outside into a cold plate network that may have your batteries or other things you have externally on it. Through your radiators, comes back through a mix valve where the mixing temperature is set. Now it goes through cold plates and heat exchangers and goes around. These are very simplified schematics. There's more to an actual flow loop than this. Once you go to a two-loop system, which is over on the right, now you add in an interface heat exchanger, an interloop heat exchanger. And so that's taking this single loop inside here and taking the energy from that, putting it into an external loop that has the same plumbing. And now you're using external fluid, which goes to the radiator. And so this is now a two-loop system. If you start doing parts count on this, you can say, yeah, so I have to buy for a two-loop system, I buy a pump, I buy an extra accumulator, buy an interloop heat exchanger. And so obviously 2 loops is heavier. So let's go to the next page. So when we talk about advantages and disadvantages of the single and dual loop system, so let's look at dual loop. It lets you optimize your internal and external fluids both. So I can get the best internal and the best external fluids. And internally, you're looking for something that has high specific heat, a low viscosity. You'd love it to be non-toxic. And of course, water checks all those boxes. So that's why we normally use water on our internals, water or water mixtures on our internal loops. External fluid, you'd love it to have low viscosity, and you really want a low freezing point. Other things are secondary, things like thermal conductivity, specific heat. You'd like those to both be high, but those are kind of secondary. Your key things are low viscosity, low freezing point. But now if we look at the disadvantages of the dual loop, you always have a temperature drop across the interchanger. On Orion, it's about 4 degrees centigrade. And so that's going to lower your average radiator temperature. So once you've lowered the average radiator temperature, your specific heat rejection drops, and you need more radiator to get the same heat rejection. And so that can result in a mass growth. If you're just growing radiator area in the absence of anything else, that's a mass growth. So as I said, you've got to buy an accumulator, an interchanger, a pump package, and also some more radiator. So that's the disadvantages of a dual loop system. So now we say, okay, fine, we've got these disadvantages. Let's look at a single loop system. And that clearly has some advantages. You eliminate the hardware that we talked about earlier. It works out to be about 100 kilograms of hardware, and that's not insignificant, especially if you're going to the moon. 100 kilograms is a big dang deal. And of course, also you've got less rotating machinery, less control valves, less things that are moving around. So your moving parts count is lower. So by definition, you've got a lower probability of failure. But if I go to a single loop system, I really want to find a non-toxic fluid, right? Remember, internally, I really want it to be non-toxic. But the only truly non-toxic fluids are water and water mixtures, and everything else has some level of toxicity. Everything else we have is something you don't want to have huge amounts of in the cabin. So I call those not toxic fluids, things like the Goldens, things like FC72. And they're advertised as being non-toxic, and that's true for a laboratory setting, but for a spacecraft, we're stiffer in terms of what we call toxicity. And so these not toxic fluids almost always have lower specific heat, about 1/4 that of water, which means you've got to pump more of this stuff. So you've got higher pump power, and that also means to keep the pressure drops down, you've got to have larger and heavier internal lines. These things also have higher viscosity. And if you've got higher viscosity than the Freons or the HFE 7200, it's very difficult to get turbulent flow in the radiator. And it works out that we'd love to have turbulent flow in the radiator to keep the temperature drop between the fluid and the surface of the radiator down. So it's harder to get turbulent flow. Also, these fluids tend to have non-ideal viscosity curves. You'd really love to have a viscosity curve that is very flat, that as the temperature drops, the viscosity doesn't go up much at all. If you got something that's going up logarithmically as the temperature drops, you run risk of having radiator stagnation, where you get slowing and stoppage of flow in a single tube or a single area, and then that would freeze if you're in a deep space environment. So we'd like to get the best viscosity curve we can, but it's hard to get in a single loop system. So What does make a good coolant? We talked a little bit about this, but let's dig a little bit more. So internally, we want low or no toxicity. We can deal with low toxicity if we do the appropriate things. If we have a trace contaminant control system that size for a leak we expect, or if we build to minimum risk, where we build to minimum leakage, we can live with something that has low toxicity. We absolutely want it to be non-corrosive in whatever material we've built into the system. And so if you're going to build an aluminum system, you want it to be non-corrosive to aluminum. If it's stainless steel, that's much easier. Love to have a high specific heat to keep the pumping down. Low viscosity, just to make it easier to pump, lower pressure drop, and high thermal conductivity to get good performance in the heat exchangers and the cold plates. And for an external fluid, the first thing is low freezing point. You don't want to freeze this stuff up. Also, of course, want it to be non-corrosive in whatever its material is and however you built the system. High specific heat is great because you have to pump less of it. Low viscosity, get turbulent flow again, get high heat transfer, and high thermal conductivity for the same answer. So everything here on this list is common between internal and external, except for low or no toxicity inside and low freezing point outside. So those are characteristics that we want specific to internal and external coolants. So this page, we're just going to talk about typical coolants we've got available. And so we look at the freezing point, which is important, viscosity, which is important, and then of course also the CP, trying to get get a high CP, high thermal conductivity, and low viscosity. So when we look at this, water, of course, is our fluid that we are typically using. And so you just kind of use that as a baseline. And you look at like Freon 21, which is what we used for the shuttle external system. It's less viscous, good. It's easier to get turbulent flow on the radiators. Lower CP, lower thermal conductivity, but very low freezing point. Freon 21 doesn't freeze till it hits -135 C, which is good and cold. Ammonia, which is the space station external system, is actually a wonderful heat transfer fluid. It's almost an analog to water. It's got lower viscosity, its specific heat is about the same, and its thermal conductivity is about the same. So ammonia on space station was an excellent choice, but if freezing point is a little bit higher, it's -78 centigrade, and so it's a little bit more difficult to deal with if you're out in deep space. We'll go through all these, but what you want to look at here is we've got HFE-7200, which is the analog to Freon 21, has about the same properties, but lower thermal conductivity, and about the same freezing point. We get to the FC72, FC770, and the Goldens, our viscosities are, they're about 1. They're in that ballpark. Again, the same specific heats, low thermal conductivities. You can see we're down about 1/10 of what we get for water, but the freezing points are low. So in terms of coolant choices, that just kind of gives you an idea about what we've got. And of course, Golden HT80 is the fluid that we're typically using these days, our fluid of choice, and FC72 is the other. And those both have good low freezing points and reasonable viscosities. So when we talk about two loop systems, water is obviously the best choice if we're going internal. And the risk, of course, is high freezing point. And that's because you have to run the water loop somewhere on the order of 40 centigrade as a return temperature if you're doing condensing, 40 Fahrenheit as a return temperature if you're doing condensation in the heat exchanger. So you've got to run your external loop colder than that to allow for temperature difference across the interface heat exchanger, and you're at risk of freezing. So that's why Orion is using a mixture of water, propylene glycol, and water. It's not quite as good in terms of thermal characteristics. Thermal conductivity is a little bit lower, viscosity is higher, but its lower freezing point gives you margin. You can also put in an additive package, which allows you to use ammonia in the system. And we do know that they're safe because they've got low vapor pressure. If you have a massive leak, you just clean it up with towels, dump the towels in the trash, and everybody's happy. So that's good for an internal system. In terms of external, as I was saying before we went through the properties, ammonia is a really good choice for a low Earth orbit because we've got fairly warm environments. But if you're going to go to deep space, ammonia is not the best answer. Also, there are ground handling issues with ammonia that they like to avoid it simply because you've got to use a lot of PPE if you're going to be loading ammonia on a system. And there are a lot of safety precautions you have to take that you don't have to take with most other coolants. So for Orion, they're using HFE-7200, again, low freezing point. The orbiter used Freon-21, and that's mainly for the low freezing point. And as I think I said before, it was designed to run with deep space facing radiators for long periods of time. They could do a solar inertial attitude for hours on end where the belly of the orbiter was pointing to the sun. So you were sitting there in a very cold environment. In addition, they were designed for a polar orbit. So you could be in a deep space environment for a very long time. They didn't have 7200 at the time. 7200 was invented as a replacement for the Freons. And I recall being, when I was a younger pup, being up in front of the engineering director. Walkeye was the ER chief and was also my first division chief before he moved over to robotics. And I was talking about cooling choices for one reason or another, and I mentioned that Freon-21 was a crappy heat transfer fluid, which it is. And Walt said, that's true, but it was an excellent system choice. And he was exactly right. That as you look at the system design for the orbiter, having to live with long periods of time with the radiator pointed to deep space, freezing point is number 1, 2, and 3. And then you make the compromises you have to make to use a low freezing point fluid. And actually, Freon-21 was about the lowest freezing points of the Freons. And when you look at the Freons, the other thermophysical parameters don't really change all that much. So it was actually an excellent system choice, worked great on the orbiter. So we talk about single loop systems. And so we're talking not toxic fluids. So water is not going to work for a single loop system because you're not going to send water out to a radiator where it can freeze. It's just a bad idea. There are also reasons not to use water glycol mixtures unless you want to go to a stagnation radiator. And we end up with issues. Apollo used water ethylene glycol, and they did use a stagnation radiator, but the mixture of water ethylene glycol they used was a eutectic mixture, so it didn't actually freeze, it more kind of slushed. So they never got to a point on the radiators where they stopped flow. The water propylene glycol does actually freeze. So if you get to a point where you get stagnation in the radiator and flow through a tube stops in a deep space environment, it's going to freeze. And once you freeze, you can't get it back just by getting flow back. You've got to do something to physically thaw it, whether it's heaters on the backside or a heat leak from an adjacent tube. So it gets a lot more tricky than what they did in Apollo. So we're talking about non-toxic fluids. We've got things like FC72, and 3M, who's the manufacturer, says it's practically non-toxic. I love that because it's practically. So what does that really mean? And then we've got the Galdens, and Solvay, their manufacturer, says there's no toxicity in their literature. But as I said before, there's a difference between not toxic and non-toxic. And for us, non-toxic means something that we can have in the cabin at levels that we can foresee. And the levels that are allowable are set by the Human Health and Performance Directorate, RSA, here at JSC. And they have a lot higher standards than OSHA, than anybody. And in fact, the spacecraft maximum allowable standards, there's a JSC document, we call them SMACs for short, gives us the allowable concentration of everything. And so it gives us the concentrations allowed for FC72 and for the Galdens. When we look at what's truly non-toxic, it's water, because you can drink water. And everything else is going to have a SMAC value that we have to adhere to. And Kayla, I saw you flash across a question. Does the saturation pressure of the fluid affect the performance? Not particularly, but what the saturation pressure does is it tells you what pressure you have to run your accumulators at if you're a single phase system, and that changes the design of your system. But it doesn't really play in terms of the performance, but it does play in terms of how how thick your tube walls and how thick your heat exchanger walls have to be. But saying that, none of the fluids that we're talking about here are particularly high vapor pressure. Even ammonia is it's about 4 atmospheres at 4 degrees C. So it's not particularly high pressure. And so it's there within the realms of pressures that we're not really particularly worried about in terms of tube wall thickness. All right, so let's look at the not toxic fluids. So as I mentioned, we've got FC72 in the Galdens. And for FC72, it is a perfluoroalkane. And so for that class of fluids, our folks in SA have established a SMAC up to 180 days. And they did not set a SMAC for anything beyond that. So we really are kind of an unknown territory beyond that, but we can work with the SMAC for 180 days. And it's 1,100 parts per million. And that sounds like a fairly large amount of stuff, but we'll talk a little bit, it's not as large as you'd like it to be. And as I said, if you recall, 3M says that this stuff's not toxic. Our folks beg to differ. They say that you can get irritated if you're in an environment of beyond 11,000 parts per million for more than 180 days. What they do is they go back to the animal studies and they start looking at the data and looking to see where the irritation where the irritation occurs, and then they back off even a little bit from that. So that these are conservative numbers that you can absolutely deal with. Now, we did ask them about the Galdens because there's a lot of, folks are looking at Galdens. They're being used in some spacecraft even today, and asked them to go look and see, well, what would the SMAC be of the Galdens? And these are perfluoroethers, perfluoropolyethers rather, which are related, but they're a little bit more reactive. And so there's really not any data in the literature. And, our folks asked the manufacturers of these perfluoropolyethers, what data they have that allow them to say they're not toxic. They wouldn't share the data. But these are related to the perfluoroalkanes. So they can't set a SMAC, but they know it's not going to be higher than the value for the perfluoroalkanes. It might be actually a little lower because these are a little bit more reactive compounds. But we're looking at things like 11,000 parts per million is our limit of the amount of stuff we can have in the cabin for a long period of time. So what does 11,000 parts per million mean? And so there's a lot of information on this chart, but it works out that we're looking at a limit of roughly 200 grams per cubic meter. If we look at, just for comparison, Space Station Nodes 2 and 3 have internal volumes of 75 cubic meters, which means that we can have up to 8 or 9 liters of these things in the cabin and still be below the SMACs. The trick is they're low vapor pressure fluids. So if you do get a leak beyond your limit, if you do get a leak beyond the 8 or 9 liters into your cabin, what are you going to do with it? Well, you're going to have to clean it up pretty quickly because the stuff is going to evaporate. And it's going to evaporate because its heat of vaporization is very low. It's about 1/30th that of water. And so you can't just clean it up with towels, because you clean up with towels, you put the towels in the trash, the stuff is going to evaporate out and get back in your atmosphere anyway. So what you really have to do is you have to limit your leaks below these kind of levels, or be able to clean up whatever leak you think you might have and still be below these kind of levels. And so we always worry about fire hose leaks. We've seen these actually on the ammonia system externally on Space Station, where a QD fails to seat and you just dump your fluid. And so you've got to protect against that in your design. So if you have an accumulator that has more than 8 or 9 liters of volume, you've got to allow for that to totally dump out of the system. The volume of the system isn't going to dump because it's a low vapor pressure fluid. That's the good answer. But you're going to dump the accumulator. So you've got to deal with that, which means now you've got to buy into having some sort of a cleanup mechanism that you wouldn't have had to have beyond the towels that they normally would carry on a water propylene glycol system. So if you look at so when we talked again more about non-toxic fluids, so I already talked about you save some mass, you save about 100 kilograms. Your radiator temperature is going to be a little bit lower, so you're going to have less heat rejection on the radiator. But, and here's the big but. So you've got to upsize the internal thermal control system lines because we've got lower specific heat. To do the same job, we've got to pump 4 times the mass. But the stuff's a little bit denser, which means you've got to pump 2.5 times the volumetric flow rate. Also, you know that the thermal conductivity is about 1/10 that of water. So that means I may well need to modify my cold plate, my heat exchanger. I might need to make the passages thicker so that I've got more thin area inside the heat exchanger. So you've got to deal with that. And anything you do there is only going to increase mass. And so this 100 kilograms of mass savings is very quickly eaten up by the fluid, the line, and the fitting mass increases. And plus you need to have an additional mass for any spill cleanup. Now, you might ask, we've had visiting vehicles that go to space station and that are okay with these kind of fluids. And the reason is that these are systems that you can test on the ground and show the leakage, and nobody is touching anything in this system while it's on flight. And so that's how we get around that the allowable leakage can be taken up by the trace contaminant control system on the space station. And so that's how we're able to use those fluids on vehicles to visit space station. If you're talking about a vehicle that has either orbital replacement units where I'm going to be plugging things in and out, or even if you're plugging in and out experiments, you're going to have the availability of having quite a bit larger leaks. And in fact, we know that all QDs leak, all soft goods leak. It's just a question of how much. And if you get a nick on an O-ring, it can leak a fair bit. And of course, you can have a fire hose leak, so you've got to deal with that. So a vehicle that has orbital replacement units, you've got a much more difficult time justifying non-toxic fluids. So if we just do the math, and we're looking for the same pump power for both water and a non-toxic fluid, because pump power is important. And so that's a goal. Just let's say, fine, we want to make the thing have the exact same pump power. So we know that the pump power, of course, is 1 over the pump efficiency, volumetric flow rate times the delta P through the loop. And so volumetric flow rate times delta P in a line is just 1/2 L over D, 1/2 rho V squared times the friction factor. Assume we've got turbulent flow. We run through the math and we find out that Q delta P is this expression. And so what we're going to try to do is to keep this the same going between water and a non-toxic fluid. And we're going to ignore the viscosity because they're similar between water and the non-toxic fluids, and you only have a 0.2 power in the previous slide, so we're not going to worry about that. When all is said and done, you come up with, to get the same sort of a pressure drop, you need to grow the diameter of your lines by 1.8. So that means not just the lines, but every fitting you've got in there, everything that touches the fluid, other than say cold plates and heat exchangers, has to grow by 1.8. And so we've got 3.3 times the cross-sectional area of the lines. Density is 1.6 times. So the fluid mass is 5 times the mass as it was in the water system. Just by comparison, when we look at the US lab internal water loops, those contain 250 grams of fluid. So when we're trying to save 100 kilograms, it doesn't make sense to spend several hundred kilograms to save it. So that's why you've got to look at the whole picture when you're looking at non-toxic fluids and single loop systems, and make sure that you understand what you're trading and what makes sense. Pause for questions. So do we have anything, Kayla?
We do have another question. Let's see. Does the saturation pressure of the coolants also affect the performance of the thermal control system?
Yeah, I talked about that as we were talking fluids.
Okay, so they already went through that. Let's see if they have any more come in.
Okay, the folks online, please don't be bashful about asking questions, because I love to talk and I'm happy to talk.
Okay, here's another one. I think you talked about this. How does toxicity affect internal fluids?
Yeah, I hope we talked about that. You know, toxicity, to me, toxicity is number 1 for an internal fluid. You know, because you can make anything work is the trick, right? But before you even start thinking about using an internal fluid, you've got to make sure this toxicity is acceptable. So that's key. Have anything else, Carlos?
No, it seems that's it. You go ahead now.
All right, let's move on. So, one of the questions folks always want to ask are single or two-phase systems. And I come at this from somebody who was involved in two-phase systems. And some folks think I'm really stubborn about this, but I'm not a fan of them for human thermal spacecraft, or human spacecraft rather. There's a reason for that. We developed two-phase ATCSs at JSC in the 80s and the early 90s. Within my branch, the branch that I joined, they had sold two-phase systems as saying, hey, these are great. Any place you're on the loop, you can get the same acquisition temperature. So wherever you are, we're going to send you saturated fluid and you get that same acquisition temperature. And that's great. And you've got a lower mass flow rate. And that's because you're using the latent heat instead of the sensible energy. And the selling point was you need about 1/10 of the flow rate for a single phase system. And of course, as I was talking about, power is important. And of course, the other thing that lets you, even if you keep the power the same by having less flow, you can have smaller lines. And so that's a weight savings there. So these were the selling points that we had for two-phase systems. And at JSC, we spent a lot of energy and a lot of time developing systems. We had 3 candidate systems for space station, went through, down selected to 1. And we're pressing forward with the use of a two-phase system. But what happens is the reality doesn't always match your expectations. As I said, we had three candidate systems. By the time we found one that was robust and that we liked and that worked consistently, all the power savings disappeared. Your theoretical power of pumping the 1/10 of your liquid through the lines, in principle, you're going to be well less than 1/10 of the power. But it ended up that we had a combined separator pitot pump that used about 500 watts of power when a single phase loop would use about 300. So it ate up all the power savings. They were gone. The other thing that happened is that the mass savings evaporated. And that's not really a pun with two-phase, but you can take it that way. And that's because even though we had said up front, you don't have to pump as much of the stuff, you can have smaller lines, the two-phase lines, the return from your heat acquisition devices is two-phase. And so now your volumetric flow rate is higher than it was going into the device. And in fact, can be hundreds of times higher if you're fully evaporating. So the two-phase lines have to get larger. And then we realized that, if we're going to start this thing up, you're going to start fully flooded. So that meant you had to have enough fluid in your accumulator to fully flood the system, to get the liquid lines flooded, get the two-phase lines flooded, and that was a lot of liquid. And then you start up and you start evaporating, you create your single-phase system, and off you go. And the third thing, and this is something that we fought fairly successfully, I thought, up through 92, when we did the space station redesign, was upper level management was really skeptical of a system that couldn't be fully ground tested. They were like, well, you've got these 1.5-inch two-phase lines. How do you know how they're going to work in space? And of course, we said, that's a small part of the pressure drop in the system. It's maybe 20% of the pressure drop in the system. We believe we can tell you the pressure drop within 100%. So, yeah, it's not going to affect it. But management, folks are always pinging on us about this. So there's another thing that comes up when you finally start thinking about this. So we were a two-loop system. So there was a water inside, ammonia outside. And so when you've got a single loop system, you see down here in this, a single phase internal loop. In your heat exchanger, in your interchanger, you can have a constant delta T across the heat exchangers you're going through. And that's how you design a two-loop system with the same m.cp inside and outside. But if you go two-phase and you've got two-phase outside, single-phase inside, your temperature difference through your heat exchanger looks like this, to where your external loop has to be colder than your exit temperature, rather than allowing it to be warmer than your inlet temperature, or pardon me, colder than your inlet temperature, colder than the exit temperature, and an average temperature higher than it is over here. And so that means your radiators actually have to get larger because they're running colder. And space station is actually, its design environment is fairly warm. It's about minus 10 Fahrenheit, I think. But we went in and actually showed that if you look at this thing, soup to nuts, you look at line sizes, you look at the mass of the fluid in the lines, you look at the radiator mass based on space station numbers, we found out that to make it break even, just for mass, and really just for mass, not even for power, you'd had to have a 75 kilowatt system with a transport distance of about 50 meters, which is equivalent to today's ISS. And what that's saying is that now if you grow this thing bigger than ISS, two-phase makes sense. ISS sits kind of on the edge of two-phase making sense. And when you get smaller, things like Gateway, which is 5 kilowatts with a transport distance of 5 to 10 meters, obviously single phase makes perfect sense. Two-phase just doesn't make any sense. And so this is the kind of thing that we learned and that I learned. And so that's when somebody asked me, do you want two-phase for a small vehicle? No, absolutely not. Unless there's some other reason that you really, really need it. Like, for example, AMS, the alpha magnetic spectrometer, uses a two-phase carbon dioxide system. But they use that because they really, really, really need a constant and uniform temperature at the sensors. And so two-phase made sense there. And so they had other issues that drove them to two-phase for their smaller system. So the other question you might ask is, well, do we want to use heat pipes? And, this is always a question that's asked. And, we, as an agency, we use heat pipes on satellites where we don't want mechanical pumps or need them, right? So if you've got a physically small satellite with a small heat load, you don't need a mechanical pump because the heat loads are low, that's good. Or if you've got instrumentation where you don't want to accept the minimal vibration that a pump puts in, then you might choose heat pipes. The other thing, on human vehicles, we might use heat pipes where we're worried about punctures from micrometeoroids or orbital debris, or if we're in the Gateway lunar orbit from just micrometeoroids. For example, the Russian segment of the ISS uses heat pipe radiators. And that actually was the place where we were on ISS early on. But our practice, so the flow-through radiators on the orbiter, we had flow-through radiators, combined 3.6 years in orbit between the vehicles, no flow tube punctures. They did have radiator punctures where they had MMOD puncture of the radiators, but never hit a flow tube. Late in the program, early in the program, these were just aluminum tubes that were bonded to a thin aluminum face sheet, so they were kind of out there. Later on, they took a thin strip of about a half-inch wide strip of thin aluminum, about 40 thousandths, laid it down over the flow tube to give it a little bit of armor. And that actually occurred after the Challenger accident, as it was phased in over time. On ISS, we've had flow tube radiators. They've been operational since 2007, no flow tube punctures, but we have bumpered flow tubes where there's a gap between the flow tube itself and the surface of the radiator. Now, we did start on ISS with heat pipe radiators, but because we were really worried about punctures. And then this was in early 90s, where we started to better understand the MOD environment. We're like, we're not looking at having a huge number of punctures. Can we get away from heat pipes? Because heat pipes are heavier than flow-through tubes. The other thing a heat pipe does is it decreases the surface temperature of the radiator because the heat pipe itself has a temperature drop as it's carrying the energy. And worked out that it was fully acceptable to go to flow-through radiators with bumper tubes. And so that was a change that was made. As a note here, and this is just something I carry around in my brain, we were starting to look at Gateway. One of the questions that the young project manager asked was, well, how about heat pipes? And I'm like, no, because I know that the deep space environment is an order of magnitude less severe than LEO. When we're in LEO, about 90% of what we're seeing is orbital debris. So just in a rough sense, when you start in walking around sense, tenth of the environment, but you can generously say that the effect of a puncture is 10 times as severe if you're in a lunar orbit. So that kind of makes it a wash. So I said, no, I don't think we want heat pipes there. Okay, and I also made a note here that you've got heat at a lower temperature than the cool at exit temperature. It's the same problem that we had on a two-phase loop. You've got the fluid is coming through a heat pipe radiator array, and it's decreasing as it goes past each heat pipe. And you've got this gap between the temperature of the fluid and the heat pipe. So that's the first thing, is you're giving up all this availability over here. So your radiator is running colder than it has to. And in addition, you've got the temperature drop in the heat pipe itself. So these are both things that just are working against you when you use heat pipe radiators. That kind of alludes to this heat input being an issue, that when you're talking about transferring heat into the evaporator, you've only got a very small area available to transfer the heat. And that's on the order of a 50th of a square meter. It's quite small. But you think about that and how many heat pipes you have. And now let's talk about a 25 kilowatt heat exchanger we have for ISS. It's got 2 square meters of heat transfer area. So it tells you that your choke point is going to be getting the energy into the heat pipe. So there's that. That increases the heat resistance. I have fluid flow resistance here. It should say thermal resistance, and decreases the radiator temperature. And so you've got that. So you're getting clobbered on giving away availability at in your radiator. You're getting clobbered on getting heat into the heat pipe, and plus you're getting clobbered on this temperature drop through the radiator. And these are things you're willing to pay if you need to use heat pipes. If you're worried about pump vibration, if you're really, really worried about micrometeoroids and things like that. So you do pay that penalty there, but just realize you're paying a penalty for heat pipes. Nothing is free in this business. So deployable radiators, and this is one of these things where I have my opinions and my informed prejudices. The great things about deployable radiators are you reject heat from both sides. Apollo had body-mounted radiators, pure body-mounted. Orbiter had half body-mounted and half kind of deployable. The forward radiators could lift off the payload bay doors a bit and get some heat rejection from the backside of the radiators. But so that's an advantage. The bad thing is you're going to add a crit 1 deployment to your activation sequence. If I've got a deployable radiator on a vehicle, those radiators have to deploy, no kidding, or I'm done. And so I just added a crit 1 deployment. And I'm a thermal guy, and the structures guys are very clever. The mechanisms guys are very clever, but they're not perfect. So now we've got a crit 1 deployment. So we can reject heat from both sides, but they're more massive than body-mounted radiators. And for example, the mass of the ISS radiator deployment mechanism, if you just take the panels and think about everything else being the deployment mechanism, the scissor arms and the cabling and the motors and all that stuff, it's double what the mass of the radiator is itself. So if you've got a body-mounted radiator, by definition, it's lighter than lighter in terms of mass per unit area of heat rejection area. The other thing that happens if you go deployable is they can't act as micrometer protection for the vehicle. And so a radiator, our typical radiator is, equivalent to about 40 thousandths of an inch of aluminum, which is about a millimeter. And it acts as a micrometeorite shield. So you put that as a body-mounted radiator, it's your shield. If you don't have a radiator, you've got to add body-mounted radiator. You've got to add some micrometeorite shields everywhere, and those tend to run 1.5 millimeters. So an obvious answer is fine. Make the radiators your shield. Add a little bit of thickness to your face sheet, which by the way is great because it increases your fin efficiency. And now what you've done is you've saved the mass of some significant mass in terms of the body-mounted radiators. So I'm a big fan of body-mounted radiators, that it lets you do the type of good system design that we should be striving for. That you try to do body-mounted radiators, and if you absolutely can't do it, then start looking at deployables. But in my opinion, your going in position should never be body-mounted radiators. And you can see my bullet down below. If you're the cavemen found out that if they needed to tan an animal's hide, what they could use is its brains. And brains actually are a good tanning mechanism. And they found out that every critter had just about enough brains to tan its own hide. And so I think, similarly, that each module ought to have enough surface to reject its waste heat, which kind of makes sense because your surface area has to do with your volume inside, which has to do with how much stuff you've got inside. And it just works out that kind of naturally your area matches up with your volume and how much ability you have. And in fact, this is the Russian experience. When they built, Mir, it was fully body mounted radiators. There are parts of space station that are in orbit are all body mounted radiators. And so the Russians have done that. And we kind of moved away from that with space station, partly because we thought, our radiators were built for 75 kilowatts of heat rejection. And you couldn't do that with the smaller modules that were inside, with them also being partially blocked by the adjacent modules and by the truss. But as it turns out, we've never used all the capability on space station. We run it somewhere around 30 some odd kilowatts rather. And so we possibly could have gotten away with body mounted radiators. Okay, so we talked a little bit about radiator stagnation, and let's talk a bit about what it is and why it's bad. So think about a radiator where we've got parallel flow, where the radiator is set up like a ladder, where we've got an inlet manifold and an exit manifold, and it's an environment that's cold. Environment that's cold enough to either raise the viscosity greatly or to freeze the fluid. So if you happen to have flow in a tube slows down. So once the tube flow slows down, its temperature decreases because now m dot is lower, the exit temperature is lower. As your temperature decreases, your viscosity increases. That leads to lower flow rates. And so it's a cascading problem where you can actually stop the flow and you can freeze it. And now this condition can now cascade to other tubes. And so if you're in a cold environment, stagnation can lead to freezing. So unless you're designing for it, it's undesirable. And early on, our design for Orion did use a single loop with water propylene glycol, but because of the behavior of water propylene glycol, there was a bear of a time dealing with stagnation. The radiator was really prone to stagnation, and so they ended up switching back to a two-loop system. It might be worth pausing here for a moment just to note that, as I said, Apollo used a stagnation radiator. And that was a decision that was made fairly early on because they were working with differences in environments going from low Earth orbit out to the deep space environment as you're heading out towards the moon. And although they kept the sun on the side of the spacecraft and had a rotation of the spacecraft around its central axis of a rev every 3 minutes, I believe, there were still times, long periods of time, where the radiators were looking at deep space. So the idea was that we'd let the flow slow down in some tubes as we were in a really cold environment or to lower heat load. And then we come back and we get to a warmer environment, flow will go back in naturally. And when you read the reports, they had a bear of a time getting this thing to work. The idea was that you had different different manifold lengths to vary the flow through each of the tubes. They were in the chamber cutting and fitting with tube lengths. Trying to do it by modeling. They had modeling that we would think of as rudimentary, but was sufficient to allow them to try to figure out what was going on in the radiator. But it was really, really hard, and they had a difficult time with it. So, generally, and then of course, as I said, once we go to water propylene glycol, stagnation's bad because it leads to freezing. It doesn't just slow the stuff down. And so now you've got a host of other issues. How do you thaw this thing and such? So stagnation is probably not a good thing to go for as your first design. Part of the thing I talked about early on was that you would like a nice flat viscosity curve. This is temperature versus the viscosity ratio. Viscosity ratio meaning the viscosity of the fluid over its viscosity at 20 centigrade. So you can see that ammonia goes up about a factor of 3 as it gets down close to its freezing point. For N21, about a factor of 4. Our HFE is going up about a factor of 8. But what's happening with things like the HT80 and FC72, they have a higher curve. So this is going to be more difficult as it gets colder. The viscosity is going to get higher. It's going to be more prone to stagnation. So you have to be aware of that. FC7770, which is, by the way, a good fluid that's not particularly toxic, has a very steep viscosity curve, so it's not real good for this application. Same thing with HT170, that it's got a very steep viscosity curve. If we were to put water propylene glycol on this chart, it would be up over here. It's got incredibly steep viscosity curve, and that's why stagnation issues were a very, very big deal when we were looking. So we talked a bit about Apollo with their parallel flow, where they had parallel flow into the radiators through manifolds of different length into these tubes that were spaced together, and then that flowed up into a second radiator where it was just a down and back. And getting these lengths were right was very, very difficult. And they spent a lot of time in the chamber, and there was a lot of white knuckle time when you read between the lines of the reports. So just in summary, plant stagnation is hard to get. And as I said, Apollo used analysis, but the testing was exhaustive and exhausting to the folks who were doing it. We're much better at modeling, but getting the details right is kind of tricky. So I think you still have to go in to test if you're going to be planning stagnation. But then if you're with modern fluids, modern allowable fluids, if you do freeze, you're going to have to work out thawing them. And so it's a different issue than what Apollo was working, but you've got to make sure you can thaw them. The other thing is that, we worry now about large heat load turndowns. We've got, for example, on Gateway, we're crewed and uncrewed, where when the Gateway is sitting there with nobody on it, it's about a third of the heat load is when people are there. And so that's a fairly large turndown. Apollo was about 1 to 1.5. So they didn't change their heat load all that much through their flight profile. So it was more the environment that was changing, but it was a much smaller operational box than what we're asking for things like Gateway to do these days. And, we often come into things where they try to get higher turndown ratios. We often say we'd love to have 10 to 1 turndown. So if it's a 5 kilowatt system, we can take it down to 500 watts of heat rejection. And now the problem just multiplies. So modern fluids, high turndown, gives you freezing and stagnation, and it just becomes a real bear. So one of the things I mentioned is you'd like low viscosity fluid for your radiator, for your external loop. And that's because you really want to have turbulent flow. And you want to have that to increase heat transfer. And what we want in a good design is that the thermal resistance through the film is much smaller than the radiation thermal resistance going out to deep space. And once you got turbulent flow, yeah, that's the case, that your driving thermal resistance is your radiation resistance going out to deep space. In Apollo, because they were using water ethylene glycol, fairly high viscosity fluid, they couldn't get away from being laminar. So they used a lenticular tube, like you can see over here. Yeah, they used a lenticular tube to increase the flow area and increase the area to get better performance, and they were able to get acceptable performance of their system. So, as I said, what you really want to do is you just want to make space the highest thermal resistance so that you drive your temperature gradients in your tube down. And so once you get into laminar flow, a couple of things happen. Once you've got your tube spacing set up, normally we do our tube spacing in the radiators at about 4 inches or 100 centimeters, because that just works out to be about the right number, gets you high radiator fin efficiency without getting, see, I lost my train of thought. I was looking at the screen. I'm sorry. So, 4 inches gets you not too heavy, because you can keep your tube size reasonably small, but also keeps your fin efficiency up. So if we look at the bottom, you've got laminar flow. So your Nusselt number is 3.66. Works out that your UA, which is up here, which is Nusselt number times K over the diameter. And then when you go through it all, it's Nusselt number times the thermal conductivity, pi times the length. So when you're at laminar flow, you are independent of tube diameter. So I can't do a trick of decreasing tube diameter to get better heat transfer. It's not going to happen, because I decrease the tube diameter, my surface area goes down, even though my convective coefficient goes up. So you're just kind of stuck there if you're laminar. But if you're in fully developed turbulent flow or laminar flow, as I said, it's a constant. But once we get to fully developed turbulent flow, we got Prandtl number to the 0.8, Reynolds number, or 0.4, Reynolds number to the 0.8. But we're in a place where we can start doing things, and we can start fiddling around with tube diameters and maybe a little bit with tube spacing if we want to do that to try to get ourselves some better heat transfer. So if we look at just a radiator fin at 13C, so that's holding it at the kind of temperatures we want to be at in a fairly cold environment, in a minus 50, minus 40 environment, and we've got a radiator surface emissivity of 0.9, fin efficiency of 1. We've got a Q prime of 18.8 watts per linear meter. So if we look at laminar flow results and we just look at over here, we've got all the fluids that we've been looking at. Over on the right is our film delta T in this condition. And so for water and ammonia, it's acceptable. It's a couple, 3 degrees, you can live with that. But once you start getting to anything with a lower thermal conductivity, and that's the break point here, you've got a very high film resistance. You've got 20 degrees centigrade. And in a T to the 4th environment, 20 degrees centigrade will kill you. Can't tolerate that sort of temperature drop between the fluid and the surface. You're going to have to do something clever. If you want to have laminar flow, you're going to have to do something clever to dramatically increase the heat transfer area of the tubes, or you're going to have to drive yourself to turbulent flow. Those are your choices. So if we look at turbulent flow doing the exact same stuff at Reynolds number 5,000, all these film delta T's have come down. If you recall, we were up at around 20 degrees centigrade for all of our newer fluids, and here we're down below 2 for everything. So I love turbulent flow, and it's something that you'd really like to have in your radiator if you can get it. So here's pause for questions. We got anything else, Carlos?
Yes, we do have a couple questions. Just want to make sure. Let's see if you've gone over these. All right. Here's the first one. How can we reduce temperature drop in the heat pipes?
In the heat pipes themselves, there's not really a heck of a lot you can do. If you're talking about a traditional axial heat pipe, you've got temperature drop through the metal. You've got a temperature drop in a axial loop heat pipe. You've got now to get the energy out through the liquid layer, the liquid typically ammonia layer, to the evaporating surface. So you're just stuck there. And then you've got the temperature drop in the condenser, which isn't quite as big a deal, but it's the same thing. You've got to get the energy from the condensing surface out to the aluminum. And then there's really not a whole lot you can do with the evaporator other than making it longer. You can do things like having a heat exchanger that encases the evaporator, and you can do some tricks to try to increase your heat transfer inside, but there's really kind of limits on it. We do very, very well on our convective heat transfer in our compact heat exchangers. And as I pointed out on the slide, the ISS heat exchanger has about 2 square meters of surface area for a really, really high convective coefficient heat exchanger. So now if we're going around the outside of a tubular evaporator for a heat pipe, you're kind of stuck. There's, you've got physical limitations of what you can put in there, and you've just got area issues. You just don't have a lot of area available. What else you got,
Okay.
Carlos?
Here's the next question. For certain gateway elements that have power and propulsion purposes, no pressure vessel for human presence, why would heat pipes be desirable?
A lot of design comes from where you've been, and it's actually a zip code thing. So the PPE is being done out of NASA Glenn, and their heritage is, what they know. A lot of it's satellites. A lot of satellites do use heat pipes because they're low power, they're small, they're they're compact, low power, and you can use heat pipes, and you avoid having to have the electrical issues of even of a pump, not to mention reliability issues and stuff like that. So a lot of it has to do with where you came from. If we had designed the PPE thermal system, I'm not 100% sure what their what their heat rejection requirement is, we may have approached it a different way. So there's always two answers, and a lot of your bent just comes from what your institutional heritage is too.
Okay, do you have more time for more questions?
Sure.
Okay, in what cases would we prefer deployable radiators over the body-mounted radiators?
Well, see, I'd never prefer them. What cases would we be driven to deployable over body mounted?
Yes.
Okay. That's a fair question. So if you can't do the job with body mounted radiators, then you're driven to deployables, right? And for example, on Gateway, there's an element that has more, its critter doesn't have enough brains to tan its hide, so it needed to go deployable. But on other elements, we've got enough surface area to do body mounted. And so, I would say it's if you don't have the surface area that you have to go deployables, then that's what you do. But deployables to me are always second choice.
Okay, I have one last question.
Okay, before you go, Carlos. So I'm allowed to tell stories because I'm old enough.
Yes.
So in fact, when we were doing the Gateway conceptual design, one of the things, and the project manager actually, and I were he knew me, and so he trusted me. And so I'm like, I want to be body mounted. I need every square inch of area on this vehicle for radiators. And so he was very good. It's like, the EVA guys were wanting a corridor for working. It's okay, how big does that really have to be? And so we were able to set aside practically all of the surface area for radiators. And that's shown in the final design. Okay, go ahead, Carlos.
Okay, here's this one's interesting. You mentioned that PGW is not a good fluid due to it having a high probability of stagnation and freezing. Both Orion and Gateway plan to use PGW. So is there a reason why it was chosen over the other fluids?
They're using that as an internal fluid. Both Gateway and Orion are 2-loop systems. So the water PGW doesn't go outside except to go to the heat exchanger. So the stagnation only occurs in the radiator. So it's your external fluid. And so the reason why we did start with a single loop system with water PGW for Orion, but moved away from that because of the risk of stagnation and the problems that it brought. So we got Carlos?
No, we got, let me see, I got another one. Let's see. In regards to heat rejection and stagnation, are there any pros and cons to using serpentine/series radiator flow tubes versus parallel flow tubes?
Ooh, that's a good question. So if you've got a fluid that could stagnate, right? You could just go a single tube that's serpentine, right? No issue of stagnation there. That's kind of that's a degenerate case, right? A single tube. You can go parallel tubes where everything is parallel like a radiator. Like that was, for example, that space station, everything is parallel. Or you could do something in between, right? And in fact, we've looked at things like for Gateway, so look to see what kind of series parallel flow arrangement makes sense, right? Do you want to do how many flow tubes in series can you get away with? And then you put stacks of flow tubes of these series tubes in, or these parallel tubes in series. So we've looked at that. The problem if it's just a single tube, of course, it gets really big because you got to keep your pressure drop reasonable. So you've got to compromise. You've got to look to see if you can keep things, reasonably close. And of course, you think about it, right? Because I was talking about stagnation. You want to avoid it. So if I only had 2 tubes in parallel, stagnation is probably not an issue. Because what I was saying was, gee, I really worry about one tube freezing and causing the other tube to freeze. Well, heck, that can't happen if I've only got 2 tubes. So you can start looking at doing things like, 2 tubes, 3 tubes, 4 tubes. And as you start growing the number of tubes in your parallel section, you'll find they start to get small pretty darn quickly because pressure drop is d to the 4th. So they start to get much, much smaller, and your mass comes down, and then you can now start looking and saying, okay, cool, let me stop flow in a tube on the edge. And just, you can take the worst case, just say, fine, I stopped this thing. What does the temperature get to? Does it freeze the tube? And is there enough conduction from the tube next to it that it keeps it above freezing? And if you find out the answer is yes, then hey, you are good to go.
Interesting.
Do we have another one?
Yeah. Let's see. What are the issues and problems associated with the high flux, high temperature heat pipes?
High flux, high temperature. Yeah, that's not really my field. If we're talking about things like sodium heat pipes, that's not my field. I really can't address that. I know there are startup questions that you've got to make sure that you deal with, because of course sodium is a solid at room temperature. But it's a whole nother field that I've not even dabbled in.
Okay. Okay, let me see. Here's another one. Can we use thermal storage to curb stagnation and freezing?
So when you use thermal storage, assuming that your thermal storage, it's an orbital case where you're changing the environments or the heat loads as you're going through an orbit. So something that's cyclic with a reasonably short time period there. Yes, thermal storage would be helpful there. More we use thermal storage to supplement radiator area, but it does have, you're right, it does have the side benefit of keeping your heat load on the radiator up, and anything you do to keep your heat load on the radiator up is going to make yourself less prone to stagnation if bad things go. That's a good question.
I guess people got confident. They're asking a ton of questions now. Okay, let's see. This is a follow-up question. NH3 is not recommended for deep space applications due to its freezing point. NH3 will be used on Orion as well. Were there any other fluids considered over NH3? Are there any concerns with freezing on the vehicle?
We didn't really worry. We didn't really want to do ammonia for Orion. Part of it was deep space. We were worried about that. Wanted the low freezing point. We actually started out with HFE-7000, which is another one of the same family of fluids. And where we got kind of stuck is that at the time we were designing Orion, we were at the end of the transition. In fact, we're still in the transition of going to ozone-friendly freons or ozone-friendly refrigerants. And so it was a question of, there was this, massive number of fluids being designed for other ideas, and what could we use to use there. And so I recall, we did have another fluid that we looked at way back in the late orbiter days as a possible freon replacement. But as far as I know, we fairly quickly settled on HFE-7000 for Orion, and then when 7200 came out, it actually had somewhat better properties, so we jumped to that.
All right, we could do one more.
Sure.
Can we use nanofluid, hybrid nanofluids in space systems? What is the future for this type of fluids?
Ooh, that touches on something I've dealt with. So when we're talking about nanofluids, what you're buying is increased thermal conductivity at the expense of viscosity. That's what you buy. So the idea is you add nanoparticles to a fluid and you get some increase in thermal conductivity because of the Brownian motion of the nanoparticles. But you also get an attendant increase in viscosity. So now we're back to the same thing about higher viscosity. My lines get bigger. I've got to deal with that increased viscosity. And what am I gaining is the question. So you think about, what am I gaining when I use a nanofluid? Well, I might be able to make my heat exchanger a little bit smaller, but my heat exchanger is already pretty darn small, right? And so I don't have an issue there. If I now have higher viscosity, and let's say I'm using that, let's say I'm using the nanofluid outside, my higher viscosity is going to make it harder to get turbulent flow, because actually our 5,000 is about as high as we get on the radiator, on the space station and on the orbiter. That's about where we run. So it makes it a little bit harder to get there because I've got the higher viscosity. So when I looked at nanofluids, they just didn't play in at system level. The bump in thermal conductivity didn't really pay dividends, and in fact, the bump in the viscosity you got hurt you. And I saw we got one more in.
Yeah, one more. This is the last one. In what situations on what spacecraft is radiator stagnation desirable?
Well, on Apollo, they were doing it because that was their way of managing load and capability. That's normally when we think about it today, we really don't want to have stagnation because it just makes our lives more difficult. We have done some looking at things like freezable radiators, which is kind of the next step on stagnation radiators, and you can build those. But then you've got to thaw them, and how do you thaw them? And surely you can put heaters on the radiators. That's good. But then of course people make fun of you at meetings because they say, "Why'd you put heaters on your radiators?" So I don't know that today we've identified a place where we really do want to go stagnation. But if you're in a condition where you really have to crank down your heat load, well, let's suppose you really want to crank down your heat load in a cold environment, and then you've got a warning that you're coming back to high heat load. In other words, they'd say you're operating in a quiescent condition, and I know that the crew is coming back, so I'm going to crank up my heat loads. So now you've got to go through your process to bring your system back. And then, of course, you probably have to do this before they launch the crew. And so you've got to build that into your system. So it adds complication. It adds operational complications, I think, mainly. And then, of course, if you're freezing and you're freezing in tubes, this brings the whole question also of tube rupture and how we deal with freezing fluids. So that's a long answer that doesn't really tell you much, but stagnation is not something that we typically are looking for these days. Is that our last one, Carlos?
Yep, that's it.
All right. Now we have a stop we're supposed to be done at 10:30, right?
Let me double check.
But the break is at 11.
Let's see. 10:30, yes.
Okay, but I think that, yeah, but there's nothing scheduled from 10:30 to 11, I don't believe.
Yeah, we have a 60-minute break, and then we start the next course.
Okay, so let's press on. I'll try to speed up a little bit, and we've got, I think, 14 more slides, so it'll take a little bit to get through. So how do you go about designing a system, right? Somebody comes to you and they say, "We're building a new spacecraft. So we need an active thermal control system for it, and go ahead, and how are you going to design this?" And I am long since retired, so they can't ask me. So now somebody else is going to do this thing. So first choice, are we single phase, two phase? That's a good choice. Are we one loop or two? What are my coolants? What does my radiator look like? I see from Kayla we're scheduled until 11, so I can speak more slowly. So choose your radiator configuration, figure out what's going out there, size your flow rates. Now calculate your heat rejection, and that's enough for a preliminary design that lets you size out what you really need for the system and what it looks like, and lets you build a schematic, lets you build a MEL, lets you build so you've got a master equipment list, you've got a power equipment list, and so you can start doing things that you do in preliminary sizing. So if we go single phase, so my guess is that it's going to be a long time before we build anything larger than space station. And as I said, space station for a human vehicle is the trip point for single phase, two phase. So we're going to be single phase on anything that's going to be done in any sort of foreseeable future. So once we've made the fluid choices, now we can define the internal loop fluid flow rate. And I would say internal, but of course, if it's two loops, it's the internal loop. If it's a single loop system, it's all the same loop, but we have to define that internal loop flow rate. So you start by saying, what's my heat load? And that will be given to you. And you need to know the temperature rise through your coolant loop. So for example, over here on the right, we've got water coolant with a 5 kilowatt heat load. I took the low temperature is 4 centigrade. That's assuming that you've got condensing heat exchanger. The 4C is about the temperature you need to use for a condensing heat exchanger. Took the high temperature of 30C. That's a battery base plate temperature. Our batteries don't like to get too hot, so you can take that as a base plate temperature. And so now that gives you enough information with these equations to just go ahead and calculate what your mass flow rate is, right? Delta T is high minus low, 30 minus 4C. The mass flow rate is Q over CP delta T. So this comes from your requirements. They tell you you've got up to 5 kilowatts heat load. These are your temperature limits. Gives you a mass flow rate of 165 kilograms per hour. And as I said, these temperature limits, even if the person who's giving you the issue doesn't know it, you have to know the questions to ask. So high temperature limits, electronics typically can get up to about 35C. They can really start to warm up. So batteries are normally the things that drive our temperature. And so that gives you a base plate temperature of 30C. Our cold plates, normally the exit temperature is about the same as the base plate temperature. So if the base plate temperature limit's 30C, 30C is your coolant outlet temperature limit. So a low temperature, of course, 4C if we're using condensing heat exchanger. If you've got a number, it's going to be a number higher than the maximum dew point if the condensation is by some other means. So if they're doing condensation by, say, an amine bed or some other unit, and now all you've got to do is take care of the sensible energy in the cabin, you can bump up higher than 4C, but you can see what happens is now my temperature drop is actually going down. T high minus T low is going down. So actually more mass flow rate. So it's never a clean thing about what is better and what is worse. But if they give you this temperature, you really want to use your higher temperature simply because that lets your radiators run hotter, right? I could say I want to, even though I'm not condensing, I'm going to send 4C liquid to my system because I want to take that full 26 degrees of temperature change through the system. But you really want to use your highest temperature simply because this raises your radiator temperature, increases their performance. So once you've got your flow rate, now you want to say, okay, how big are my tubes? Because somebody's going to ask you how big are the tubes, how do I package them, and so on. So when I do this, I think of the pressure drop as being roughly 4 equal parts. You've got pressure loss through the tubes themselves, bends and fittings, control valves, and heat exchanger and cold plate pressure loss. And I do this more for the sake of simplicity because tubing pressure loss, I can calculate, right? That's easy enough. I can look in the back of any fluids textbook and figure out how to do tubing pressure loss. Bends and fittings are hard, control valves are hard, heat exchangers and cold plates are hard. So just calculate tubing, multiply it times 4, and you're going to be pretty darn close. And so now you want to size the tubing. And so you need to know the pressure drop. I've got mass flow rate, which gives me volume flow rate. And I need to know the pressure drop. And so we do, at the pump, we can do 3 to 4 atmospheres. That's our typical way of doing business. So you've got that. You have to guess the transport length, which means you have to take your module and kind of sketch out where you think the tubing is going to go. And you can do some very simple sketches using just the diameter and the length of your module and guess at what the overall tube size is going from the pump outlet back to the pump inlet. And now you just figure out what the diameter has to be, knowing that you've got 3 to 4 atmospheres of pressure drop available, and off you go. And just by way of letting you know what's out there, so on the orbiter, the internal water loop had a 3.6 atmosphere pressure rise. The external loop was 4.9. That's why I say use 3 to 4, and that's probably pretty darn close. So now if we're doing an external loop, so a single loop, not a single loop, but a 2-loop system only. So what we want to do for an external loop is we absolutely want to match m.cp between the internal and external loops. And the reason you do that is so that you have a constant delta T through the heat exchanger, which keeps your external loop temperature highest. So your radiator temperature is going to be somewhere near your average external loop temperature. So the more you can do to keep that up, the better you are. If you have too little flow outside, you're going to have to come in colder. If you've got too much, you're not going to come out as warm as you could otherwise. And in fact, on Orion, the way that it's built is they do have more flow than you would do in this ideal case. So their external loop temperature is actually a little bit colder than it would be otherwise. So how do you size the radiator? So what we normally do is we just say, fine, rather than building up a full-up model, we can just take the arithmetic average between the inlet and the outlet temperatures of the external loop and take that as our fluid temperature. And that turns out to be pretty darn close. So we just use the arithmetic average, take a fit efficiency of about 0.95, and that's going to account for both the convective and conductive heat transfer. And that's assuming that you've got high heat transfer inside, meaning you've got turbulent flow. That assumes we've done a reasonably good job of our radiator fin and getting high fin efficiency. That's reasonably close. So calculate the average sink temperature. And then it's fairly easy, once you know the average sink temperature, to calculate the specific heat rejection and the radiator area you need. It's all just fairly fundamental heat transfer, right? So you've got your specific heat rejection has to do with your emissivity, fin efficiency, which we said is 0.95. Stefan-Boltzmann constant, radiator temperature, and sink temperature. So that's fairly easy. So again, going back to our 5 kilowatt example, once I've calculated my specific heat rejection, I can tell how much radiator area I need. And then I can look back to see if I've got enough on the body for body mounted radiators and make sure that everything is good. Same thing for if we're doing 2 loop, but now we have to include the Elm to D for the heat exchanger. Preliminary sizing, 4C is probably good. ISS, we actually did better than that. We were at 3 Fahrenheit or 1.7 C. So, you can use 4C for sizing, and then you go through and you get the exact same kind of an equation to figure out what your specific heat rejection is. So I kind of brushed over what the sink temperature is. And that gets to be probably the biggest part of your problem, is trying to figure out what your sink temperature truly is. And so you can start by looking at a cylindrical radiator and a side to sun orientation. So let's just look at a cylindrical radiator. By coincidence, this is what Gateway looks like. It's a body mounted cylindrical radiator. Side to sun is your sizing case. So take the optical properties I have listed here, take the solar constant, and so you've got an absorbed solar energy, and that's easy because it's just alpha times the solar times your projected area of the module, which is standard, times the length. Emitted IR is emissivity, fin efficiency, which we're taking as 1 when we're doing a sink temperature calculation. Again, just T to the 4th, and then your area is pi times D times the length. So it's the total area of the module. Setting them equal and setting 8 equal to 1 gives you a sink temperature of 234K. So that was the number that I showed you earlier, but this is where it comes from. It's a cylindrical module. That's your average sink temperature. So it's worth just noting here that that's the average over the whole vehicle. So if I'm side sun in a cylindrical radiator, part of the radiator that's not facing the sun is going to be seeing deep space. So it's going to be right cold. The side along the belt line that's facing the sun is going to be quite a bit warmer than 234. But on the average, when I'm doing radiator sizing, I just have to look at the average sink temperature. So when we just look at a preliminary radiator design using the same kind of things we did earlier, and doing 234 Kelvin as the sink temperature, for a single loop, we find out that we need 25 square meters of radiator area. We go dual loop because we're taking the temperature drop across the interface heat exchanger. We now need 28 square meters, or about 10% more. So going dual loop is costing me 10% in radiator performance. But again, realize that if I still got enough surface area, a lot of that area is free because I'm not having to buy micrometeorite shielding. I'm just putting radiator, which is very slightly more heavy than micrometeorite shielding. So it's very nearly free to buy additional area if we have it available. So That's sizing. And now let's talk about radiator bypass. You know, in the original schematics I showed you, we were going around, we had the radiator, we sent part of the flow through it, part of it comes out cold from the radiator, we mix it with some of the warm flow from the inlet to maintain our set point. And so let's just look a little bit at radiator bypass, and this is just worthwhile looking at just to kind of see what happens when you just do a radiator bypass. So for a halo orbit, if we're looking at something like these lower orbits here, the sizing case is going to be side to sun in the warmest approach over the lunar surface. And this is, so my warmest approach is actually about here, where I'm at about 45 degrees from the equator. And so I get the most IR from the surface, and then I'm side to sun. And so I've got solar energy plus IR that I've got to deal with. The cold case is going to be when we're in deep space, and that actually happens when you're, you know, when you're near the moon, getting IR from the moon and albedo from the moon, which we also need to worry about, is fairly short in terms of time. So you're going to be deep space most of the time, and when you turn nose to sun, that's going to be your coldest because you're just going to be seeing deep space all over the vehicle. So here we're just going to ignore lunar IR and albedo. It's significant, but it's also complicated, so we're just not going to do it here in this example. Talk about a two-loop system with a constant 4 degrees C interchanger LMTD. Let's just run through the performance here on how the radiator bypass works. So, cylindrical radiator, again, same optical properties we had before, T infinity of 234. Now we're going to have a fin efficiency of 0.95, like I was saying earlier. So now I've got the temperature of the stuff coming in. Part of that's going to be bypassed to maintain an outlet set point of going to be 4 degrees C. Or I think it might be lower if we're doing a two-loop system. So we know what the mixed temperature is. The mixed temperature is just a weighted average of the radiator bypass temperature, which is the temperature of the inlet temperature, and the radiator outlet temperature. And what's going to happen is this bypass fraction is going to be adjusted just to maintain the mixed temperature. But it's this bypass fraction that we're going to look at. So how much of the radiator how much flow gets bypassed through the radiator, how much is actually going through. So at the design heat load, and if I just look at the distance through the radiator, so I'm going through the radiator, what is my temperature of the fluid as I go through the radiator? And this is from a very simple Excel model, but it does show what we want to show. So at x equals 1, so this is design, come in at 26 because we are taking the 4 degree drop across the interchanger, go out at 0. Again, 4 degree drop across the interchanger. So now what happens as I change my heat load? So I go to 75% of my heat load, and again, at this same environment, 75%, I'm actually doing 62% of the stuff goes through the radiator. And its temperature at the outlet drops. At 50%, we're only going 35%. What's interesting here, now let's go to our 10 to 1 turn down. I've only got 6% of flow through the radiator, and I am coming out at the sink temperature. So this is what I'm trying to show here is that with radiator bypass, it's nonlinear. That is, you start cranking down on your radiator flow and doing more bypass as your heat load gets lower. What happens is your outlet temperature gets lower, so you have to crank down more. So you crank down more on your radiator flow, then your load goes down. It's not linear. So it's something that feeds on itself. So now what if we go to a 0 Kelvin sink? Full load, we're looking at 27% flow through the radiator, coming out pretty darn cold. As we get down to the lower heat loads, as we get down to 10% heat load, we're down to just 1% of the flow through the radiator. And we are coming out really cold. We're coming out somewhere like minus 170 Kelvin. And so now we start looking at the freezing and pour points for our fluids. And let's look at 7,200. That's minus 138. So that's going to be roughly here. So if we go below the blue line, which is 50% heat load in 0 Kelvin sink, and get anywhere close to 25%, which is the red line, we're at risk of freezing. And that's without stagnation, that's without any monkey business in the radiator. That's just with radiator bypass. And this is just what happens when you get to a 0 Kelvin sink, is that the nonlinearity of a radiator bypass drives you to getting very, very cold radiator temperatures at lower heat loads. So you've got to be aware of it. So this is what happens when you do radiator bypass, which is what we did on Apollo, on shuttle, on space station. But why does that happen? And it's because it's the average radiator temperature that's setting the heat rejection. That if you set up and you look at the heat rejection is going to be integral over the area of the local heat rejection, or the average temperature is just going to be the heat rejection divided by some constants plus T to the fourth is your average temperature. So if you think about it, if I've got so many kilowatts that I've got to get out of the radiator, that says what my average temperature has to be. And so that is just physics. You can't just change that. So if I'm going to have stuff coming out cold, if I'm going to go in warm and I need a cold average radiator temperature, I have to come out really cold. So what we can do is do a different style of thermal control, which was actually done on Gemini originally, which is a regenerator bypass thermal control. So the trick here is, what if we could bring in the fluid that's colder? In other words, put a bypass heat exchanger in line so my hot fluid coming out of my module gives up its heat to the return fluid and brings that up so that I can lower my inlet temperature to the radiator. So while maintaining the same average radiator temperature, my outlet temperature now comes up and I'm not as much at risk of freezing. And so that's the idea of the regenerator bypass set point. So here the idea is that you have a regenerator that you're flowing through and you bypass around that to change your set point. As I said, it was first used on Gemini, and the reason they used it was that they were going to a very high altitude where they weren't seeing much of the energy coming from the Earth. They were very much in a deep space altitude. So they wanted to keep the flow up through the radiator. So what this does is it gets your flow through the radiator to be very high and to be almost constant as you're going through, even at low heat loads with the radiator very cold. You keep your flow up so that your delta T across the radiator is small and your average temperature can stay high with maintaining fairly high temperatures in the radiator. So you can really only use this for two loop systems. And the reason is that when the radiator starts to get cold, you're not really maintaining full flow because stuff gets more viscous, your flow slows down. But that doesn't matter if you slow down the flow in the external system because you've got excess capacity in your interloop heat exchanger at low heat load, so it's all okay. We did have this as the original baseline for Orion, but they were able to show by detailed analysis that they were okay with radiator bypass, that their combination of sink temperatures and of heat loads in their operating envelope was okay for just doing a radiator bypass. Of course, if you start to get, and that's the advantage that you start with something that you don't, usually when you're designing, somebody wants the world. Your project manager wants the world. They want to be able to go from huge range of heat loads to huge range of environments and stay at both of them forever. So, the answer is, yeah, if you want to do that, you've got to buy a regenerator. You've got to buy that mass of a regenerator. But Orion was able to show that, their envelope had shrunk enough, their operational envelope had shrunk enough that they were just fine. And that's my last slide. So Kayla, do we have any more questions?
Yes, we currently have one. It says, do we account for fouling during preliminary design?
Good question. Of course, we would like not to foul. The short answer is no. Because fouling means you've messed up, right? That you've done something where you've got some fouling in your tubes that's undesirable. So no, we typically don't do that. But if you think about what would fouling do? So where am I fouling? I'm fouling in the heat exchanger, and yeah, that's a big deal. Because if you foul in the heat exchanger, you're plugging things up, you're covering surfaces, it's getting ugly. So in the radiator itself, probably not a big deal because your biggest thermal resistance, if you've done your job right, is going out to the space. So we typically don't worry about it. We try to worry more about maintaining materials compatibility. Like when we're designing, when I was doing the gateway preliminary design, and I have water propylene glycol, I was assuming my tubing was stainless. And by the way, it does work out that there is very, very thin wall stainless out there that they used on the orbiter that is not that huge of a mass increase over aluminum. And so Orion did start aluminum. I believe they've gone to all titanium. But you can get very thin gauge wall tubing that is not that much of a mass hit over aluminum. Do you have anything else that came in late, Carlos?
Yes. In regenerative configuration, is it possible to place the RHX at the radiator inlet?
Okay, so I just pulled the slide back. So the radiator inlet flow goes through the regen, goes through the radiator and comes out here. So it flows, you have a choice of either flowing through the regen or of bypassing the regen to maintain this temperature where you want to be. Today we would probably put the flow control assembly over on the right side, on the warm side, just so you're not controlling this crazy cold fluid, just for materials compatibility and your control valve and such like that. But it's transferring heat between the radiator inlet and the radiator outlet. Anything else late breaking?
Yep, here we go. This is a career question.
Ooh.
What's one piece of advice you'd give to fluid and thermal engineers who are early in their career?
And it's a piece of advice that was given to me early in my career, so I can pass it. Jim Jacks, who was, he worked on Apollo Soyuz and was one of my first high-level managers. He said, Gene, he says, when somebody asks you for an answer, make sure you ask when they need it. And then you build your analysis based on the timing that you've got available, because you can build an analysis that is most wonderful and gives the exact answer, but if it's a week late, it doesn't do anybody any good. So build your assessments to your schedule. And it's harder to do these days when we've got softish deadlines, right? I mean, on Orion, there are deadlines and they're building to that, and Gateway, there are deadlines, but they're a little bit soft. But it's a little bit hard to do that. It was much more critical when we were doing things like, it does become more critical when it's flight, right? So if we have an issue on space station and we need to do analysis, it has to be quick. And it has to be of the fidelity that you can do within the time available. And then you've got to make sure you advertise what your fidelity is. And the other piece of advice I would give is make sure you're right. The only thing worse than a late answer is a wrong answer. And there's a lot to be said for simple calculations. And those who know me know that I don't deuce into Fluent, which is kind of funny because I was a contract monitor on it for about 8 years. Huh. But there's a lot you can do with pen and paper. There's a whole lot you can do with Excel. And so what I tend to do when I build models is I'll build them in Excel because we don't do Fortran anymore. But then I will check them with pen and paper. And so the pen and paper obviously is not going to give you the right answer, but it tells you if your model is giving you the answer. And we have to be careful. There's a lot of artificial intelligence out there, but we have to be careful it doesn't become artificial stupidity. And you need to check, we build these huge models and you just need to check it and make sure it's giving you the right answer. And there are a number of times that I've seen model results where I'm like, that just doesn't seem right. That just doesn't look right to me. And then you do a simple pen and paper model and show that no, that's not right because there was an error in the model. There was something, or more typically, there is something in the code that pops up that hadn't popped up before that the code developer had built, and it's not the way that you thought you were modeling, but it turns out that you're modeling it some other way. So that's a couple or three things, I think.
Okay, I think we don't have any more questions. Thanks a lot, Eugene. This is very informative. This is a great presentation.
You're most welcome. I'm glad I could do it.